Hello everyone. So here in this video we will learn a complete simulation of a system where we have a permanent magnet, a strong permanent magnet, and it is placed close to a thin plate that is made of iron. Okay, so when the magnet is placed close to the thin plate made of iron, it will get deformed and it will get attracted towards the magnet, because we have a permanent magnet and we have a thin metal sheet. So the amount of deformation and other properties we can study using simulation. So in this tutorial we will learn how to model these systems. So without wasting our time, let's get started. So welcome back to Comsol Multiphysics. This is the first interface of the software as you launch it. So in this full tutorial you will have a complete simulation workflow, starting from geometry, adding physics and so on up to the post-processing. So this video might be a bit long and I hope that you will watch the full video to get an understanding of how this works. This model is actually an example model, but I thought why not make a step-by-step tutorial so that people who are just starting out can easily follow along and learn how to model. So I always prefer to use the blank model over model wizard. So I will just create a blank model. Blank model is basically creating a new file in any software. So I'll just click on blank model. So when you click on blank model, you will have an interface something like this, where you have a model builder window. Model builder window is basically the details of the file. So you have the file name, global definitions, results. If you add different physics, settings and everything else, you will see in the model builder. So this window is basically the settings window. So whenever you click an option, the settings of this particular option will be shown in the settings tab. And then we have the graphics tab. So here you can visually see the geometry, mesh and results, and also the plots. Similarly, you can have other tabs such as adding physics, adding study and so on. At the bottom you have the message, progress, log, table, maybe if you add probes, the probe data and so on. And at the top, just like Microsoft Office, PowerPoint or any other software, you have different options such as home, geometry, physics, mesh, study, result, develop, etc. Okay, so this is the very quick introduction to the interface. Now the first task is that we will now add the physics in the model. So we click on add physics. The add physics tab is here, but nothing is showing up. Why? Because we have to add a component. So at first we'll go on and click on add component, and then we will add a 3D component. When you add a 3D component, if I go to physics, now you see that all the physics are showing up because we have the physics for the relevant component. Okay, now what we will do, we will now go on to structural mechanics. In the structural mechanics, we'll scroll down and we will go to electromagnetic structural interaction. Now we will actually go on to magnetomechanic interaction, and in the magnetomechanic no current, we will just right click and click on to add to component 1. It might take a few seconds and the physics will be added in the model. You'll see that automatically you will have a moving mesh, solid mechanics and other physics that is added in the model. Okay, so in the study we are interested to study the stationary properties of the system, so we'll add the stationary study in the model. Now the basic structure of the system is ready. Now slowly we can add different parameters in the model and create the geometry. Okay, so in the next section we will add up the parameters in the model to create the geometry. So we'll go on to geometry and we'll click on the geometry tab. Now we are interested to create a work plane. So we'll click on work plane. So in the work plane, we are actually interested to create a quarter of the magnetic geometry. Now in the settings of the work plane, let us locate the plan definition, and we are interested to work in the ZY plane, right? And the X coordinate will shift it to 0.01 and we'll click on build selected. Now we have a plane. As you can see, the direction, this is X, and we have the plane in the ZY. Now inside of work plane, you have a plane geometry. So this is basically the blue region, okay, the two-dimensional blue region where we will draw the two-dimensional geometry. That's why you have a mesh-like structure. So this is basically a 2D plane. Now we are interested to make the geometry. So we'll first draw a circle. So when you click on plane geometry, you have this option. Now let us first add a circle. When you click on circle, you will have the different settings here. So we'll draw a radius of 0.04 and the sector angle to 90 degree. If you click on build selected, you see that you have a circle. So basically you have 1/4 of a circle with radius 0.04 meter. And we are actually interested to change the position along X to a finite offset. So we'll offset this design by 0.06 meter and we'll click on build selected. Now you'll see that the circle gets shifted to 0.06 along the x-axis of this plane. So if I go back to the work plane, so it is along the x-axis of this plane that you have to remember, okay? Otherwise you will make mistakes. So what I mean by that is, in the plane, when you have the xy plane, this is along the x-axis of this plane. Now let us create one more circle. So we'll just right click and click on duplicate. And let us change the radius to 0.02 and again click on build selected. Now we have a circle, something like this. Now we are interested to actually make some Boolean operation in the geometry. So what we will do, we'll go back to the work plane. In the work plane tab, we'll go to Boolean in partition and click on difference. Now in the object to add, we'll select C1. Now in the object to subtract, we'll select C2. Now this is done. Now we will add a rectangle in the model. To do that, in the work plan, click on the rectangle. In the width, type 0.05 and height 0.02. And in the position section, that is along Y, it is offset by 0.02 meter. And you see that we have this rectangle here. Now again we are interested to duplicate this rectangle. So we'll just right click on duplicate to duplicate the rectangle. Now in the settings of this new rectangle, we'll change the width to 0.01 and the position to be 0.05. Okay. And let us click on build selected. Now we have the nice structure. Now let us go back to the geometry, click on build all. So we have this two-dimensional geometry. Now in the workplane 1, we can click on extrude, and in the extrude distance let us type 0.01 and click on build all object. Now you can see we have a nice geometry, three-dimensional geometry. This will be our permanent magnet. Now let us go back to geometry once again and click on a block. Now we are actually interested to set up the dimension of the block. So instead of writing the values directly here, let us use some parameters in the model. So we'll have dm 3 mm. So this is basically the distance to magnet. We have HP, that is 1 mm. This is the plate thickness. Then we have LP, that is 20 centimeter, and that is the plate length. And we have WP, that is 6 centimeter. This is the plate width. And we have H, that is 7 centimeter. This is basically distance to bottom wall. Okay, so now we have the parameters set. Now I'll go back to block 1, and in the width we will write WP by 2, depth LP by 2, and height HP. In the position, we have to change the Z to minus dm plus HP. Do not worry, I will explain everything what is going on. Now we'll click on build all object. So we have this geometry. Okay, so what is happening here is that we have the magnet, we have the plate, and there is a finite separation between the two. So why did we change the Z value? Because if you see that Z is along this direction, so negative direction means that it will have a gap. So this value represents the gap between the magnet and the plate. Okay, so this is almost done. Now in the geometry we'll again add a block. Now in the block we'll change the width to 2 times WP, depth to be LP by 2 plus WP, and height 0.2, and the Z to be minus H. We'll click on the build all, but before that we will add some layers here. So the layer 1 is H minus 2 times dm minus HP, and layer 2 is 2 times dm plus HP, and we'll click on build all object. Now you can see that this is actually a box. So we have a magnet, we have the metal, and we have a air domain. Okay, so the layers are basically making a boundary here. So both sides are empty, and here you have the metal plate. Now if we click here, the transparency tab, you can actually see the layers, the metal plate, and the magnet, right? So our geometry is almost done. So now we will add materials in the model. So to add material, you go on to the materials and we'll click on material tab here, and we'll click on add material. When you click on add material, you should have a tab something like this. You can always drag this, put it in the center so that you can have the material tabs here. Now inside of AC/DC, click on soft iron without loss, right click, click on add to component 1. Now again go to material, inside of AC/DC go on to hard magnetic materials, click on sintered NBFEB grades and click on N35. Just right click, click add to component 1. So we have the two materials that is added in the model. Now let us go on to the materials. In the N35, let us select domain 6. Now we also have to add air material in the model, so we'll go on to add material, click on build in, right click air and click on add to component 1. Now for air, we'll select domain 4, 2 and 1. So we'll clear the soft iron and we'll select the domain for the soft iron, and we'll select this and this. So now we have the magnet, air and the soft iron. So the material selection is almost done. Now let us slowly move on to the physics of the model. Now in the model builder window, let's go on to moving mesh. Let's go on to the deforming domain 1 and let us select domain 2, because we are actually interested to see the deformation in this domain. Now inside of symmetry roller, let us select boundary 4 and 5. Now the symmetry roller is important because generally we use symmetry roller node on flat boundaries of deforming domain, which are also symmetry plane in the model, or where you otherwise want to prevent boundary nodes from moving out of the plane. This allows the mesh to move tangentially to the symmetry roller plane but not in its normal direction. So this is quite important. Now let us set up the solid mechanics settings. Now let us go on to the solid mechanics, and we are actually interested to study the solid mechanics of domain 3. So we'll zoom on and click domain 3 only. Now right click on solid mechanics and click on fix constraint. Now just reposition the model properly and select the 29 boundary. So this is the fixed constraint. Basically this end is clamped virtually. Okay, now we also have to add a symmetry. So again right click, there should be a symmetry here. You have to click on symmetry, or what you can do, you can go on to physics, inside of physics go on to boundary and then choose symmetry. So let us add the symmetry planes. Just zoom in and select these two. So now that we have set up the solid mechanics, now the next part is to set up the settings for magnetic field, no current, that is the MFNC. Now just go on to the magnetic flux conservation, and here choose the BH curve, the magnetization model to BH curve. Now we have to add a magnetic flux conservation. So we'll go on to physics, then inside of domain we'll add magnetic flux conservation. So we'll select the domain 6 for the magnetic flux conservation, and in the material type we'll choose solid, and inside the constitutive relation BH in the magnetization model choose the remnant flux density, and here set up the value of E vector, that is 0, 0 and 1. Now again we'll go on to domain, click on magnetic flux conservation, and now we have to select domain 4, 2 and 1, basically the magnetic flux conservation for air. Okay, now we have to add a symmetry plane, so we'll go on to boundary and click on symmetry plane. Now let us select the symmetry plane 1. So we'll select one by one of all the faces that is pointing on this side. So we have 1, 4, 7, 11, 14, and then we have 17, 20 and 23. Okay, so this is fine. Now we have the symmetry plane 1. Now again we have to create another symmetry plane for the other side. So we'll go on, click on symmetry plane 2, and in the symmetry plane 2 we'll do the similar thing, that is we are going to select all the planes in the model that is pointing along the minus y axis. Okay, so here we have 2, 5, 8, 12 and 15. So our physics is almost done. So now we'll go to materials, click on soft iron, and we are interested to see the settings for the soft iron. So inside of material contents you have the different settings here. So in the Young's modulus, let us type 200 GPa and Poisson ratio 0.29 and density 7870 kg per meter cube. Something is wrong, so this is 7870. We have kg per meter cube. I hope this is fine. Yeah, so we have the details for soft iron. So we are going to the home bar and we will add a parameter. So we have a second set of parameter. In the second set of parameter, let us write the new variables here, that is AP. This is the accuracy parameter, and then we have Hmax1. This is 5 mm to 2.6 mm times AP. So this is the meshing parameter. Similarly, we have Hmax2. I'll just copy this expression and I'll just copy and I'll paste, and I'll change the values to 20 and this to be 10, and this is again the meshing parameter. Okay, so this is done. Now we are going to create the mesh and set up the mesh elements. So why we are doing all this? This is because we need to create the mesh carefully in this domain to accurately measure the phenomena and deformation that will be happening due to the magnetic field. So now we will go to mesh. I'll go to mesh, and in the boundary let us choose a free triangle. Now in the settings of free triangle, so we are actually interested to select the surfaces that will be interacting with each other. So here I'll just click the transparency, and it is actually difficult to actually choose the surface here, but I will try my best. One thing that can be done is that I can actually hide the surface, right? So if I click and hide and select the surface here, yeah, now I can actually see the surface. So if I select this surface and the surface of the magnet, so these are the two surfaces that I need to select to create the free triangle. And I'll just reset the hiding. I don't want to hide everything here. Now one more setting that is needed to be done for a free triangle is that I'll just right click on size. Now in the element size, let us choose custom, and in the maximum element size, let us set up to hmax1 that we have set up in the parameter. Now in the mesh, click on swept, in the domain selection region, click on domain, and here you can click on the paste selection and type 5 to 7 if you are following the same model, and you will see that the selection of the domain will be done. Basically the magnet will be selected. Now in the swept, right click on distribution, select 7 and click on remove. So here in the distribution, type 10. Now again, right click on swept one, click on distribution. Now we are interested to select domain 7 and we'll click on 2, that is the distribution to 2. Now in the mesh, we'll again create a swept mesh, and here we'll choose the domain, and we are actually interested to select the domain 2 here. Okay, so this is domain 2. So we'll again go on to mesh 1 and create a swept mesh, and we will select the domain here, and we will manually select the domain 3. Now we'll right click and click on distribution, and here we'll select the number of element to 3. So we are almost done to create the mesh. Now again we will go on to mesh 1 and click on free tetrahedral. In the free tetrahedral, right click to add a size settings. Now we'll choose custom and we'll set up the maximum element size to hmax 2. Now our settings are almost done, so we'll click on build all to build the mesh of the model. As you can see, the mesh is quite efficient and we don't have any unnecessary mesh here and there. Only at the end of the metal plate there is a dense mesh, otherwise the mesh is quite nice. This is because these settings are from the default comsol model. That's why it looks so perfect. Otherwise, if you are working on a new model, it might take some time to actually get the optimum value of the mesh. So now that you have set up the physics and the mesh, the final part is to set up the study of the model. So the first step is to add a parametric sweep in the model. So we'll go on to study, click on parametric sweep, and in the settings click on the add button, and here in the drop down list we will select DM and we can write the values that we need to sweep. So let's say we want to sweep 7, 5, 4, 3, or maybe 7, 6, 5, 4, 3. Okay, and the parameter value is in millimeter. So this is the basic settings for a parametric sweep. Now in the study toolbar, click on show default plots. Now in the parametric sweep, if you go on to the output while solving section, we want to plot the plot group, the different plot group we have. So the default is set to stress solid. Now our settings are almost done and we are ready to visualize our model. Hello, so we are back. So I made a small mistake here. In the symmetry plane, there are two symmetry planes and both are 90 degrees to each other, right? So at the symmetry plane, the physics is basically n dot h equal to 0, and on the other it should be n cross h equal to 0, right? Because both are in the other direction. So the symmetry plane 2, we need to set it to antisymmetric. And then so now I will click on compute and check the results. So the simulation is done and we have our results. So now we need to make some changes in the dataset to actually visually see the results. So we are actually exploiting the feature for the symmetry in the model to actually visualize our results. So in the dataset, what we will do, we will go on to the dataset and we will now go on to results. In the results, go on to more dataset. Inside of more dataset, you have to choose mirror. Now click on mirror 3D. Now as the term suggests, it basically mirrors the solution across a plane. You can either have a quick plane or a general plane. So for now we are actually interested for a quick plane. Symmetry along YZ plane. Now we'll change the dataset to parametric solution and then we'll click on plot. So as you can see that we have a dataset that is actually mirror across the YZ plane, right? So we'll rename this to YZ plane. Similarly, we'll again go to results, more dataset, mirror 3D, and then in the dataset we will select the mirror YZ plane and choose the XZ plane, and we'll click on plot. So now what actually happened is that we solved the one section of the model, we mirrored the solution, so this is the YZ plane, and the whole plane we mirrored across the XZ plane. So then we have the 4 sections, okay, and it looks like a complete solution of a full 3D salt magnet without actually compromising the computational cost. So we'll rename this to the XZ plane. Now let us calculate the dataset for another XZ plane. So we'll just duplicate this, and now this will be anti-symmetric, okay. And what we will do, we'll go on to the advance, we'll click on the define variable, and in the vector transformation we'll select anti-symmetric and we'll click on plot. So we won't visually see this change because here the plot is basically the volume of the data that is being saved in the dataset. Now in the parametric solution, the frame will choose material. So let us now look at the results for the simulation. So we will first see the default plot of stress. Now in the dataset we are going to select the XZ plane, and in the volume let us select the unit to MPa, and we'll click on plot, and now we have this nice plot, and you can already see the deformation that is happening in the model. Now to visually understand better the deformation, we'll right click the volume 1 and we'll select deformation. Now here these are the different components, and we have the scale. So we'll choose the scale to 2 to actually or let's say 1.3 to actually see the deformation change. As you can see here, the metal plate has bent towards the magnet. So now let us go to the magnetic flux density norm. We have a plot something like this, so I'll click here. Now in the dataset we'll choose the XZ antisymmetric. I will click on plot, and we see that we have a plot something like this, but the plane is shifted along X. So let me see in the multi slice here, the X plane, let us type 0 and click on plot. Yeah, so now the plane is at the center, and there is a problem with the Z plane also. So Z plane will type minus dm and click on plot. Similarly, the Y plane, it's fine, we can leave the Y plane as it is, or let us set the Y plane to 0 also. So now I hope that the planes will be at the center cutting each other, or if we don't want, we can actually remove the Y plane so that we can have this structure. So we will make a 3D plot again to actually calculate the displacement magnitude. So we'll just duplicate the stress solid and we will write this as displacement solid. I'm just following the default model that is provided by comsol to actually make this, so I'm not discovering anything new. That's why I'm trying to follow as it is. Now we'll go to the volume, and in the expression click on insert expression, and here you can write solid dot displacement, and in the unit instead of meter we can select millimeter. You can click on plot. You can see that it is a nice plot and it shows basically the color represent the displacement. So you can always change the color to thermal to actually see the change. So higher the lighter color, higher is the displacement, right? So now we'll go to definition and we'll go to non-local coupling and we'll choose maximum, and we'll choose domain 3, that is the metal plate in the maximum. So now we are also interested to calculate the force calculation for post-processing. So inside of the physics, we'll click on the domain and we'll click on force calculation, and we will select 3. If it is difficult to select 3, we can type 3 and click on OK, and we will keep the settings unchanged. So now we'll go to the study and click on update solution. We can check the progress. It might take few seconds to update the solution, and the solution is updated. Now let us go on to result. So in the home we'll click on add plot group, or we can go on to result and click on 1D plot group. So here we can write this as displacement. We'll choose the dataset to parametric solutions, and we will right click on the global solution, and in the global solutions, since if you remember we calculated the maximum displacement, so what we will do, we'll go here, and in the expression we will just paste this, and in the bracket we'll write W by dm and the unit in percentage, and here we will write maximum T by W by dm. So we'll click on plot, and we have this plot here. Now you can always change the levels. So we have the maximum displacement in percentage from the distance from the magnet. So when the distance to the magnet is small, the displacement is high, as you would expect. And of course you can change the style and the style of the line. So in the width, let us change to some higher thickness. So this is basically the displacement graph. Now we'll also calculate the total force. So we'll go again to result, click on 1D plot group, we'll write the force, and we'll again create a global variable. So here in the expression we'll type force, and you'll see that you should have a force along the z-axis. And since the total force will be 4 times, so we solved only 1/4 of the model, so this will be 4 times that, and we'll click on plot. So we have a point in the force. We'll again choose the parametric solution and click on plot again, and now you see the force with respect to the distance from the magnet. We can change the thickness of the lines. so that we can visually see the force. So we are pretty much done, and we have the different plots. So we'll go back once again. At first, what we did, we added the physics. So we had this 4 physics here. Then we created the geometry of a magnet, a metal plate surrounded by air. We set up the very basic physics. We changed the material properties. We created the mesh smartly using the parameters so that we have the minimum number of mesh element and we get quite accurate and close results. To do that, we set up the free triangle, and we also set up the shift mesh and the free tetrahedral along with the different size settings of the mesh. Okay, and also we set up the maximum and minimum size of the element so that the solution converges properly. And after that, we set up the parametric sweep and solve the model. We got the result, but to make the result more realistic, we mirrored the solution across the 2 sides, and we set up the antisymmetric property due to the effect of the magnetic field here. So here you have to remember that you have to choose antisymmetric if you are making a symmetry on the other side. And then we actually plotted the result, calculated the displacement and the force, and finally we are done. I hope that you learned how to model this kind of simulation in COMSOL Multiphysics. And if you like my effort to create these videos, do subscribe to this channel and also give a like. It helps me to keep my motivation to create more quality tutorials for you all. Thank you for watching and have a nice day ahead. And also if you are interested, you can check my COMSOL Multiphysics courses. Those are detailed courses with assignments, and you can have one-to-one help related to the course. So do check it out. The links are there in the description. Thank you all and have a nice day.